So our goal for today is to review and to practice with optimization. And I have an announcement to make, and that is that optimization. And the announcement that I have to make is that we will be canceling Thursday's homework. And the reason for that is that I hoped we'd get fairly far along in the optimization, and we'd be able to apply that to a business situation. So all of Thursday night's homework is about using optimization to maximize revenue, minimize costs, that kind of a thing. And it requires learning a special set of vocabulary and so on and so forth. And I plan on teaching that on Thursday, but based on what we did in class today in third period, I think we want to just stick with what we're doing for now. And so that's fine.
So we don't have to worry about Thursday.
Yep. So, with that in mind, let's review how the optimization goes. Our goal is to find a function f of x on a domain, and having done so, then to use either the critical point endpoint analysis that we talked about on Monday, or to use the argument from the sign of f prime that we talked about yesterday. Now let's talk about each one of these here. If I am using the critical point endpoint analysis, then I am identifying candidates. And my candidates are the critical points and endpoints. Of my domain, and then I evaluate f at each of the candidates. The largest value is the max, the smallest value is the min. Notice that in order to do this, I have to have endpoints, which means that my domain has to be a closed bounded interval. So this is a necessary condition in order to be able to use the critical point endpoint analysis. For the argument from the sign of f prime, on the other hand, I'm going to find the critical points. Find the critical points, and then I am going to create a well-labeled number line for f prime. And if it is the case that f prime is positive for x less than c, and f prime is negative for x greater than c, then f of c is a max. And that corresponds to a number line that looks just like this. So that f is increasing up to c and decreasing thereafter. If, on the other hand, f prime is negative for x less than c, and f prime is positive for x greater than c, then f of c is a min. And that corresponds to a number line that looks just like this. And notice that we don't really have to memorize this language, because this language is simply saying in math words what the number line is saying. All I'm doing is saying that f prime is positive for x is less than c, and f prime is negative for x is greater than c. So if you have the number line and you can write that down in words, you've used the correct language. And that's nice. Notice, however, that in order for this to work, it has to be the case that I only have one critical point. that at least one critical point where f prime changes signs, right? Because if I have a number line that looks, for example, like this, C1, C2, positive, negative, positive, then f prime is increasing on this interval, and it's also increasing on this interval, and I'm not really sure whether f of C1 is a max or whether f goes larger than that. Yes?
So, in this case, we can't use argument first.
In this case, you would not be able to use the argument from the sign of f prime. That's right. So a necessary condition for the argument from the sign of f prime is that there is only a single critical point. Yes, sir.
Can you use that to find the minimum?
No, because unfortunately, you might think that f of c2 would be the minimum, but notice that my function is increasing there. So it could be that my function looks like this, right? And then that doesn't help. Now, fortunately, the number of situations that show up where we do not have a closed bounded domain and we have more than one critical point are uncommon, and you won't see them for our purposes. And they happen in life, and when they do happen in life, you use some common sense. Usually, you can embed your domain in a closed bounded interval, and that.
For that situation, we can apply local maximum.
That's right, you can. Because for the local max, all you are doing is taking a look at x's that are close to c, and you're excluding everything else. And so for that reason, all you have to worry about is a sign change at x equals c for the local maxes. When we get to global maxes, we have to look at the entire number. Great question. Okay? Let's practice. I want to start with number 15. And in number 15, we have a triangle with sides A and B. Has included angle theta. What value of theta gives the triangle maximum area? Now, before we get started, let's walk through our process. We need a function, we need a domain, and then we need to choose critical point endpoint or argument from the sign of f prime. Function, domain, choose your method. Okay. So, they give a hint also in this problem. They tell you that the area of such a triangle is 1/2 times a times b times the sine of the angle between. Well, this is wonderful because it has dropped into my lap a function. I now have area as a function of theta. In fact, it's probably best to write it as area as a function of theta. Don't be fooled by the a and b. A and b are constant values. They are given to you as part of the problem. So the idea here is that I'm going to have a segment A and a segment B and an included angle theta, and I'm going to change the angle theta, and as I do, the area changes, and the question is what value of theta will give me the max area. So I have a function already, check. Next I need the domain. The domain is a set of all possible angles that we could have here. What's the smallest possible angle? 0. Technically we cannot have the angle 0 because our triangle disappears. But we can take and embed that in the closed bounded domain 0, 2. What's the largest angle?
9.
180. I can go all the way over here. But that's 180 degrees, and we don't do degrees in this class, and we really do radians. How many radians? Oh, exactly. So my domain is 0 to pi. Now, if I want to use the critical point endpoint method, I'm going to have to embed that domain in the closed bounded interval 0 to pi. And there's nothing wrong with that. Okay, so we have a function, we have a domain, now we have a choice to make. Do we want to use the critical point endpoint method, or do we want to use the argument from the sign of A prime? He likes critical point endpoint. Okay, it's what we learned first, so it's the most familiar. I'm actually going to do it both ways so we can compare them, but critical point endpoint works for me. Remember that if we're doing critical point endpoint, we need to identify candidates and then evaluate. Go. Identify those candidates. Okay, we're back. What candidates did you choose? Zero. One. Oh, pi. Pi, right. The cool mathematicians all use radians. Now, it's actually not just a matter of style, it's a matter of actually the trig functions only have their proper derivatives that you know if we are measuring those angles in radians. If we're measuring them in degrees, we end up with a scale factor that is awkward to work with. Yeah. Are there any other candidates? Yes, we have to find the critical points. And so we find A prime of theta, which is 1/2 AB cosine theta. Set that equal to 0. Notice that none of these factors can be 0, so it must be that cosine theta is equal to 0. Which means that theta is equal to pi over 2. That's not the only solution on the entire real line, but it's the only solution in our domain. Now that I have 1, 2, 3 candidates, I evaluate the area at 0, the area at pi, the area at pi over 2. 1/2 AB sine of 0. What is the sine of 0? What is the sine of 0? 0. Yeah. What's the sine of pi? 0. And what's the sine of pi over 2? 1. So that I get 1/2 AB. Which one of these is clearly the max? Yep. Which means we have the max area. I want to do something now. I want to add an additional step, especially as you're learning. Find a function on a domain and then choose critical point or endpoint, argument from the sign of f prime. And the last thing that I want you to do when you're done with each of these problems is to take a minute or two to reflect on the meaning of your answer. I do this as a matter of habit. And what it does is it helps to forge the mental connections that you need in order to understand what's going on. Let's go back and do that in our case here. Reflect on the meaning of the answer. We had these 3 candidates, 0, pi, and pi over 2. And they correspond to triangles that look like this. If theta is actually 0, then what I have is no triangle at all. I have a degenerate triangle in which A and B overlap each other. And so it has 0 area. Oh, that makes a whole lot of sense. Meanwhile, if I have an angle of pi, then I once again have a degenerate triangle, really a line segment, which has 0 area. And as my angle increases from 0 to pi, then my area will change. And right at pi over 2, where I have a right triangle, then the area is exactly 1/2 base times height, or 1/2 AB, and that is the largest possible area that I can have. So that's reflection upon the meaning of the answer, and what that does is to help get a clearer picture of what I'm doing here. I saw a lot of nodding heads when I was doing this. Didn't you find that helped make more sense of it? And all I did was reflect on the meaning of the answer.
If you're gonna use it, we can't use it because.
Great question. If I have an open interval right here, then the endpoints are not technically in the domain, and it makes no sense to evaluate at those endpoints. So, what I did was to take the open interval and embed it into a closed bounded interval so that I could use the critical point endpoint method. This problem could actually be done with either method. So now that we've solved this problem, I want to come back and solve it the other way so that you can see, and then we can talk about which one might have been better. If I do an argument from the sign of A prime, I'm going to begin by finding the critical points. A prime of theta, as we previously found, is 1/2 AB cosine theta. And I set that equal to 0 to get the critical points. And that gives me a single critical point. Theta equals pi over 2. The single critical point is the necessary condition for a successful argument from the sign of A prime. And so now I'm going to evaluate A prime. Of course, I have a domain here, which is 0 to pi. I'm going to evaluate the sign of A prime for x's that are less than pi over 2. Pick any theta that is less than pi over 2. One that I can evaluate. 0, could do 0. Pi is probably, pi is way over here. That's tough. You know the sign of 1? Pi over 4 could work. 0 also works, right? It doesn't matter. If I pick an angle that is in the first quadrant here, what is the positive or negative sign of the cosine of that angle? The cosine of that angle is going to be a positive number, right? So for any angle in the first quadrant, A prime is going to have a positive sign. What about angles bigger than pi over 2? Negative. That's exactly right. And so now I have enough information to make my judgment. A of pi over 2 is the max. Why is that? Because now we're just going to take this number line right here and write it into volts. How do we do that? That is definitely not how we want to do that. And here's why. If I say the sign changes at pi over 2, all I'm doing is taking and looking at a local neighborhood at pi over 2. And when I look at a local neighborhood, what I get is a local max. Yeah.
F prime is
Not
increasing. A prime's increasing.
Nope. Not
Greater
a-
than 0.
Is greater than 0.
When x is less
Not x.
than theta
Yep.
is less than
Mhm.
and A prime is greater than 0. I mean less than. When theta is greater than.
Yep. Okay. Notice that Mark fell prey to both temptations. And so that's a good learning opportunity here. The first temptation is to confuse positive with increasing. A prime is not increasing. Yeah. A prime is actually decreasing. It is A that is increasing. A prime is positive. And all I have to do is to read that sign directly off of the number. Second, he started to use the variable x here. But x is not the variable in our problem. It's theta. So you need to be careful about your radius. So, which one do we like better? Here's my, in blue, here's my critical point endpoint method and the work that I had to do for it. In green, here's my argument from the sine of A prime and the work I had to do for that. Which one do you like better? You like the second one? How many of you like the first one better? Second one? Jennifer, you did both. You like the second one? Okay, yeah. I find a lot of people like the second one because it kind of reminds them of the first t-test and it makes a little more sense. But I could go either way. In my life, I've gone back and forth about which one I like better. Well, we want to reflect on the meaning of our answer. And the meaning of our answer is a little bit different than it was the last time. Last time, we took a look at each candidate and what the area was for each candidate. Now we're going to look at this in terms of a changing triangle. We have a line segment A, we have a line segment B, and they form a triangle. So, theta. What's going to happen is we are going to change theta by literally rotating the segment out. And as I rotate this segment out, at first I increase the area of the triangle, which is reflected in the fact that A prime is positive, until I reach the critical point pi over 2, which gives me a right triangle. And thereafter, as I increase the angle more, I'm decreasing the angle of the triangle, so that my area increases and then it decreases with a max at pi over 2. Does that make sense? Yes?
Because endpoint can be a max.
Endpoints could be a max, theoretically. Right, yes, not in this case.
So can we still use max argument?
Yes. You can use the argument from the sine of f prime on a closed bounded interval. If you do, for example, let's suppose that for whatever reason, my A prime number line had looked like this. So that I have something like that.
It's not an endpoint.
That's right. Right. So in this particular case, if I'm looking for a max, then I really only have two candidates I need to worry about. One of them is right here. The other one actually is right here, because it could be that my area is decreasing from the max down to whatever AHC is, right? So if my function looks like this, then my max will be an A, and if my function looks more like this, then my max will be a B, right? So when I have a situation where my number line is doesn't give a clear answer, right? Then I have to consider candidates.
So you have to use clear.
You'd have to use the critical point. Yeah.
What do the graph is there?
Like that?
Yeah.
Then it's not a function. Problem solved. Good question. Okay, let's take a look at a second one here. I want to take a look at number 9 from your book. A rectangular plot of farmland. Well, let me type this up. Mark, will you read it out?
Will be bounded on one side by a river and the other three sides by a single strand electric fence. With 800 meters of wire at your disposal, what is the largest area you can enclose, and what are the dimensions?
Okay? So, here we are. Now remember our plan. First, we're going to try to find a function, and then its domain, and we're going to choose between critical point endpoint or argument from the sign of f. So, that is our goal here. So somehow, what we have to do is we have to take all of this information here and turn this into a function. Guys, honestly, this is the challenging part, is to create a function with our bare hands. And to do that, I recommend a well-labeled diagram as your tool of choice. What are we talking about here? Let's draw it. I want all of you to draw a rectangular plot of farmland that is bounded on one side by a river. What happened there? That is bounded on, it really thinks that's misspelled? Huh. It's bounded on one side by a river and on 3 sides by electric fence. Go ahead and draw that.
Thank you.
Yep. The drawing should be fairly straightforward. Here's our river. And here is my electric fence. And I need some labels. How shall I label this?
X and Y.
X and Y. Notice that this is X also because I have a rectangle. Now, on this side, I think the presumption is that the river is going to act as a boundary to keep the cows or whatever. In real life, you wouldn't do that. You put an electric electric fence along this side also because cows are dumb. And they could end up, going into the river somehow, drowning, etc., etc. They're not amazingly dumb as animals go, but they can be dumb enough to get themselves in trouble. And they can also swim at times. So in any event, this is what the problem says, so we're going to go with it. Now, the next thing, so we've taken care of this part. Put a mental check by that part right there. The next thing is to translate this. With 800 meters of wire at your disposal. What does that mean? Can you put that into simpler English words, first of all?
The perimeter, it's on that tracker, but, so it's gonna be 2x plus y. Is it?
Okay, fair enough. He just went straight to the math. What I wanted to get at is, this is trying to say you have 800 meters of wire. Yep. That's what it's really saying. And so Mark translates that as 2x plus y has to add up to 800. We call this either an auxiliary equation, we'll talk about this in the Latin word auxiliary, help, or we can also call this a constraint, and it is a constraint because it constrains or prevents my x and y from being arbitrary. If I choose a value for x, like say 100, then y has to be 800 minus 2 times x, or say 600, right? So x and y are constrained or related to each other by that equation. So I have come up with an auxiliary equation. Now we go to we've taken care of that. Now we go to our next phrase here. What is the largest area you can enclose? Aha, I see a word that signals mass. What word is that? Largest, exactly. And we put the largest area, and so that tells me the function that I'm trying to construct, and I'm going to label that as area. And what is the area in my well-labeled diagram? Hint, what shape is this? So what's its area?
X times y.
X times y, that's right. Don't give generic answers, give specific ones in terms of the diagram. Yes, sir?
On one side, that's not nice.
The one side is not straight. You're right, because I drew it And in real life, the river would not be straight. However, in real life, also, we would consider that to be a pretty darn good approximation. So if I were using calculus, what the farmer here is trying to do is he's trying to use calculus to project ahead and say, okay, I've got 800 meters of wire to use. How can I use it so that I can get the maximum amount of grazing land for my animals? Yes, that's exactly right. He's going to assume that this is a rectangle. And in fact, the problem encourages you to think of it as a rectangle. It tells you it's a rectangle. In real life, we accept that there will be imperfections in my rectangle that will make this answer only approximate. But for the mathematical idealization or the model, we take it as a rectangle in areas. Good. Now that I have this area function, it's a function of two variables, I need to substitute in order to get rid of one, and the material for substitution comes from the constraint right here. I'm going to solve for the easiest variable to solve for and substitute away. What's the easiest variable to solve for here? Y is equal to? And therefore, the area as a function of x is equal to x times y. And it is often helpful to simplify. What is the meaning of this area of x? The meaning of this area of x is if I pick a certain x, say 100, then y will be 800 minus 2 times that, which is, say, 600. And the area will be then 100 times 600. So this gives me the area just as a function of x. And now the farmer can choose mentally to change the value of x and see where the critical point is that gives him the maximum area. So, what's the domain for our problem? What is the smallest possible value of x that you could choose? 0, right? If you choose 0, then what we essentially have is we're taking this really skinny strip of land all along the river, and he's going to use up all 800 meters of wire, just putting it right on the river's edge. Pretty clear he's going to get 0 area out of that. What's the largest value of x that you can have? Good, that's right, because he has to have top and bottom as x. Each x can be at most 400. And that would correspond to a really skinny strip of land going this way, perpendicular to the river, which has no height to it. So our domain then is 0 to 400. And I'm going to use the critical point endpoint method here. You like it the best, and it seems to be pretty easy for this problem.
It's close.
I'm sorry, I said it wrong. I'm going to use the sign of f prime argument here, because you like it the best. That's the one you said you liked the best. My mouth got away from you there. So I'm going to use the argument from the sign of a prime here, and it's pretty easy to do in these circumstances. We begin by finding the critical point, by taking the derivative, setting that equal to 0, and when we do, we get x equals 200 as the solution. Let's check a number line. If x is, say, 100, and I plug it into my equation here, I find it easy to use the factored form to plug into. 100 times 600 is going to be positive. Oh gosh, thank you. Let's back up and do that right. There we go. If I choose x equals 100, here it is, then 800 minus 400 is a positive value. There it is. I got this right in the other class. I was just distracted here. If I choose a value of x that's larger than 200, say 300, 800 minus 1200 is negative. And so I can conclude that a of 200 is the max. Now we need our magic language. Who can give it to us? Jason.
Prime. That's greater than 200.
No. Positive means greater than
Oh, 0.
0, yes.
What's the difference? X is less than 200.
Mhm.
Oh, a prime is less than 0 or x is less than 200. Greater than 200.
Yeah. You probably would have written it correctly, even though he said it funny. Finally, we need to make sure that we've answered the question here, because the original question asks, what is the largest area and what are the dimensions? And I didn't really answer those questions. I found out that x equals 200 maximizes the area. But what is that actual area? So the area comes out to be 80,000 square meters worth of area. And the dimensions are the x and y. And the traditional way of writing that is 200 meters by 400 meters. But you could also say x equals 200 meters and y equals 400 meters. Either one of these, here or here, could be a good way of specifying the dimensions. And notice what went with every single one of my answers here? Units, exactly. Yes, sir.
Well, if I want to use the first
Yes.
sense,
Yes, you can.
I have to choose the
That's right. You have to embed it into a closed interval, which is fine. All that you're doing is taking the extreme values, the limit points, as being part of your domain.
So can I change all the change?
As long as it is bounded. But if your domain is 0 to infinity, not so much. Right. Yeah. Well, I want to consider now a more challenging question, number 20. And what's challenging about this one is coming up with the function you wish to optimize. In number 20, Jane is 2 miles offshore in a boat. And wishes to reach a coastal village six miles down a straight shoreline from the point nearest the boat. She can row 2 miles per hour and walk 5 miles per hour. Where should she land her boat to reach the village in the least amount of time? Okay. Oop. Now, let's draw a picture so we can understand what's going on. Here's our shoreline, and Jane is out here, and the village is down here. Now they have this phrasing 6 miles down a straight shoreline from the point nearest the boat. That's really awkward phrasing. Let's see what it's saying. What it's saying is, if I go on the shoreline to the point that is nearest to the boat, then the village is 6 miles away from that point. The village is 6 miles down the shoreline from the point nearest to the boat. It's pretty awkward phrasing, isn't it? But it turns out it's probably the most efficient way you could have said it. 6 miles down the shoreline from the point nearest to the boat. Okay. And we also are told that she is 2 miles offshore. And we are furthermore told that she can row 2 miles an hour, but she can walk 5 miles per hour. Now they ask a really interesting question. Where should she land her boat to reach the village in the least amount of time? Now the reason this is a question at all is that she is a lot slower at rowing than she is at walking. So if she were to go straight there, then she would use the least amount of distance, but it wouldn't be the least amount of time because she's relatively slow at rowing. If, on the other hand, she were to row straight into shore and then walk, then she would possibly be going more distance than she needs to in order to minimize her time. And so what's going to happen is that her optimum point, her critical point, is going to be somewhere here along the shoreline so that she can row and then walk so that the total time is the shortest time. Now, you say, she's not going to sit there and do this calculus problem. But you know what? If she has an onboard navigational computer, that computer is going to do that calculation for her like that. And we're going to be the computer. Does that make sense? What's your row? Row, row, row your boat gently down the stream. Yeah. Okay. So how are we going to do this? I noticed that I don't have anything to give me a handle on the problem yet. I need some labels. Since I don't know where she is going to land, I'm going to call this distance right here x. And I'm going to call this distance, therefore, 6 minus x. Because by landing, she divides the 6 mile distance into 2 parts. Does that make sense? And now, I can say that what I am trying to optimize here is the amount of time. I want to minimize the amount of time as a function of the point x where she lands. So this is really interesting. In physics, we do x of t all the time, right? Now we're doing t of x. And what is that equal to? Well, it is equal to the amount of time that she's going to take rowing plus the amount of time that she takes walking. Let's do the easy one first. Yeah. Okay. The amount of time that she's going to take to walk is going to be the distance that she walks divided by the rate that she walks at. And the distance that she walks is 6 minus x. And the rate that she walks at is 5 miles per hour. Now let's do the slightly more challenging one. The distance here that she rows is the hypotenuse of a right triangle, whose legs are 2 and x. So this distance is going to be the square root of 4 plus x squared. And so I can take the distance that she rows and divide it by the rate that she rows at, and that is the amount of time it takes her to row. Okay, so we've identified a function t of x. Now what we'd like to do is to identify the domain. And it seems pretty clear that the domain here, well, we can include 0 and 6. That the feasible domain is 0 to 6. The actual possible domain is anywhere from negative infinity to infinity, because she could choose to land anywhere she wants, but she is not such a great fool that she's going to land somewhere down here or over here. So the feasible domain is really 0 to 6 for this problem. So we want to consider now critical points, and then based on the critical points, we can make a choice if we want to do the critical point endpoint method, or if we want to do the argument from the sine of t prime method. The critical points are going to be slightly ugly because we have to take a derivative here of, with respect to x, of root 4 plus x squared over 2 plus 6 minus x over 5. That turns out to be not so bad. If I go term at a time, then I can pull out my factor of 1/2 and take the derivative of the square root of 4 plus x squared, and take out my factor of 1/5 times the derivative of 6 minus x. In the first case, root 4 plus x squared is just 4 plus x squared to the 1/2, and we know that derivative, but don't forget the derivative of the inside times 2x. And in the second case, the derivative of 6 minus x is just -1. Let's clean this up a little bit. We see factors of 2 that can cancel, and this gives us x over 2 roots 4 plus x squared minus 1/5. And all of this now has to be equal to 0, or possibly does not exist. However, we observe that the denominator here never vanishes. How do I solve this equation? Well, actually, it's not so bad. If I add 1/5 to both sides, then we can do a little bit of cross multiplying. We get 5x is equal to 2 roots 4 plus x squared. And now we can square both sides to eliminate the square root. 25x squared equals 4 times 4 plus x squared, or 16 plus 4x squared. And this gives me now 21x squared equals 16, and x squared is equal to 16 over 21. So that x is equal to the positive root of 16 over 21. We exclude the negative root as being outside the feasible domain. This is kind of a yucky number, and I wonder whether or not the original problem writers intended for it to be a big deal, to be a number that was quite so ugly here. If we express it as a decimal approximation, then what we get is 0.8729 miles. And we can do that either as an exact value, root 16 over 21, or as a decimal approximation. Since I got a single critical point, it makes a whole lot of sense to do an argument from the sine of t prime. So I'll set up my single critical point here with the domain 0 to 6. And now I'm going to go back to t prime, which is all the way back here. And I'm going to consider substituting a value that is less than my critical point. Remember that my critical point was 0.8729. And so an easy value to substitute would be x equals 0. If I choose x equals 0, then t prime of x is t prime of 0 is pretty clearly -1/5, and therefore I get a negative sign over here. What about when, what about an x that is larger than my critical point? How about x equals 1? If I choose x equals 1, then t prime of 1 is going to be equal to 1 over 2 times root 5 minus 1/5. That's kind of challenging to evaluate. So I would probably use a calculator to evaluate this, although I suspect strongly I'm going to get a positive value. And sure enough, when I do, I get a positive value that's around 0.05, like so. And so from this, I can conclude that she should land at x equals 0.8729, which is the square root of 16 over 21 miles, because t prime is less than 0 for x greater than 0.8729, and t prime is greater than 0 for x. I don't put that sign. There we go. T prime is less than 0 for x less than 0.8729, and t prime is greater than 0 for x greater than 0.8729. And just double check, you saw in what I just did there that it's easy to mess up your greater than less than signs. Check that we have the right signs for each one, and we're good. Let's reflect on this. What's happening? What our answer is telling us is that if she lands at any point x that is less than the critical point, then she's going to spend too much distance walking. And if she lands at an x that is greater than the critical point, then she's going to spend too much time rowing. And where she minimizes her time is by striking this compromise at an x that is at 0.8729. Well, I hope all this is helpful to you.